हेलो स्टूडेंट्स, नमस्कार सभी को. So it is written on the board applications of Gauss law. In last videos we have discussed about Gauss law and derivation of condition and mathematical expression and total flux due to closed surface which is enclosing some charge, or you can say total flux through the closed surface which encloses some charge. So we have gone through important points also regarding Gauss law. So here application is what we have to find out electric field due to what? Due to continuous charge distributions. So I am going to consider three distributions, okay, a linear charge distribution, a surface charge distribution and a spherical charge distribution. I am not saying this is volume charge distribution, but effect is same. If spherical charge distribution is there to outside points, it has same effect as volume charge, uniform volume charge distribution. So first we have to consider this thing, linear charge distribution, and linear charge distribution, this is a continuous charge distribution we are considering. It is infinitely long charged straight wire. Here wire may not be there, wire may be absent, but a fine line of charges may be there. Okay. Suppose large number of point charges are distributed along the line. There is no metallic wire or material wire, but point charges are there. So point charges are distributed along the straight line, and length of this line is very long. It extends from this infinity to this infinity, okay, lower infinite to upper infinite. So we can guess the electric field, or you can see the electric field due to this distribution at any point. And here we have also pointed out something, electric field at any point, actually it is due to charges in the neighborhood of this point, okay. Very charges at large distance will not influence significantly to this point, but still this electric forces have long range, they have infinite range, but in practice what we do, we ignore the effect of distant charges because they have very small influence in comparison to influence of nearby charges. So we can guess here electric field at any point here. Suppose we can consider a point P. Let this point P is here, point P, okay, near this is point P, okay. So you can find out electric field, or you can see the effect of electric field at this point. So suppose this charge distribution has positive charges, and electric field due to each charge will be in outward direction, radially outward direction. So large number of charges are there, means you can say this is system of charges, and at this point electric field will be due to all charges. Here electric field will be resultant of electric fields due to individual charges at this point. So electric field at P due to this charge, let us mark here A, B, C, D, okay, A, B, C, D, and suppose F, G, H, and so on, okay. Another a distant point you can say Y, let this is, and this is point is U. You can take care, I am not saying you have to choose specific point. So at P, electric field due to charge near A, okay. So each and every charge will offer electric field to this point. So at P electric field due to charge in this region A is what? It will be outward, like this. And see, it should be radially outward because charge is positive. So, electric field at the same point P due to charge which is near B in the region B. So, according to the influence we see here, this is electric field due to B. So, from P this point is slightly larger distance in comparison to distance of A, and so this is electric field due to charge at A. Here electric field due to charge at B, and this is C, point C. So, charge in the region point C, in the region of C, this will also have some electric field at P. So, direction of this field is like this, E, C, okay. And so, in same way, here I have written G. So, see, electric field, now this point is somehow away from this point P in comparison to distance of A. So, this distance is more than the distance of A. So, field due to charge which is near G, it is here, okay, in this direction. So, this is field due to charge near G and H also. So, field due to charge, field at the same point P due to charge here in the region H. So, this is there. So, a symmetry seems here, okay. Actually not seems, it is there, a symmetry is there. You can consider this charge, a distant charge also. So, this charge will have electric field at this point, it is very small and in this direction. So, this field is very small, okay. So, you can choose another charge here, electric field at this point, electric field at P due to charge near U, and this will be like this, okay. So, these are electric field. So, overall these all vectors, they are showing that electric field will be where? Electric field, it will be perpendicular to the conductor, in the direction perpendicular to the conductor, and since this charge is positive in the distribution, and this electric field will be radially outward. So, everywhere it will be radially outward. You can take point P here or here or here, take the distance same here. So, P is here at the same distance or at this point or at this point or at this point or at this point or at this point. So, at the same distance you can take point P anywhere in the neighborhood of conductor or near the near the distribution. You will find electric field radially outward. Now, remember to apply Gauss law around the charge distribution to find out electric field. What do? We imagine a Gaussian surface. So, this surface, what is this surface? Either it encloses the whole charge distribution or a portion of charge distribution. So, charge distribution is infinite. So, we will consider a Gaussian surface which will enclose only a part of distribution. And what should be shape of Gaussian surface? So, shape should be what? So that shape of Gaussian surface should be such that the electric field near any surface element of Gaussian surface is either parallel to that element or perpendicular to that element, or shape may be of any type if electric field is 0 in that region. So, what are options here? I have taken already here, I have drawn figure, okay, same distribution is here, it is drawn already. I have imagined this Gaussian surface which is cylindrical and it encloses L length of this distribution, okay. So, L length means L length of distribution having some charge. Okay, let charge density is here lambda per unit length, lambda charge is there. So, charge enclosed inside the Gaussian surface imagined is how much? L into lambda, because L is length, per unit length charge is lambda and total charge on length L is L lambda, and what is happening there? And this total charge is enclosed by Gaussian surface. So, we have discussed about enclosed charges. Whatever be the charge outside the Gaussian surface on any side, here or here, okay, there may be many charges outside the Gaussian surface, they will not affect the total flux through the Gaussian surface. This flux is due to charge enclosed by the surface. So, outside charges are not the matter of discussion here. What are the charges? What is the charge enclosed by Gaussian surface? We have to consider. So, suppose this charge density, linear charge density is what? So, we are going to find out electric field due to electric field due to infinitely long charged straight wire. Okay, here straight wire, maybe wire, because practically it is possible to charges so that they can reside. You will consider a material medium or a wire. So, there is infinitely long charge straight wire and electric field due to this we have to find out. So, okay, this is Gaussian surface which is coaxial to this distribution, or you can say axis of Gaussian surface is coinciding with the distribution. So, consider what? A Gaussian surface, okay, Gaussian surface, cylindrical, okay, cylindrical Gaussian surface of length, how much? Of length L, and it is coaxial to the distribution. Okay. So, if linear charge density is what? Linear charge density of distribution is lambda, okay. Then charge enclosed by this surface, then charge enclosed by Gaussian surface equals lambda L, okay, this is lambda L. So, Q enclosed is lambda L. So, from Gauss law, you know, total flux due to enclosed charge is what? It will independent of shape and size of Gaussian surface. So, total flux due to this charge enclosed from Gauss law, total electric flux due to charge enclosed, okay, charge enclosed, okay, it is how much? So, electric flux through Gaussian surface, okay, flux it is here through Gaussian surface due to charge enclosed is what? you know this thing, phi equals q enclosed divided by epsilon naught if this distribution is kept in the vacuum or free space. So this thing can be written what, q enclosed what, lambda L, so lambda L upon epsilon naught. Now let us proceed another way, to another way. So let us proceed to find out to electric flux or to count electric flux from the surface. So you know total flux, but total flux from the surface, from the closed surface, okay, closed surface, it is how much, phi equals closed integral E dot ds. ds is surface element, area of surface element, okay. And here you have to go to, here three faces are there, a curved surface and the plane flat surfaces. So circular face and curved. So you can write same thing here, flux E dot ds, where, through the curved surface, curved plus E dot ds, again this is flux through what, circular face, okay, plus again another circular face is there, E dot ds, and this is circular face, okay. So there are three faces, circular one, the top one is circular, bottom one is circular, and this side surface is curved surface. And so before writing this, we could write here what, electric flux through a small surface element, electric flux through small surface element, a small surface element you can write. So this is method of counting flux or method of calculating flux. It is how much, d phi equals E dot ds, okay. Now see on the figure, so I am going to calculate flux. So this is what, this is surface element of area ds on the curved surface, lateral surface, this is surface element. So this d phi is here, d phi, flux is scalar quantity, but E and ds both are vectors. So we are seeing the flux here through this surface only, surface element only. So ds area, the flux through this area is what, E dot ds. So this is d phi. So d phi flux is here through this surface, through surface element, and d phi from here, d phi from here, d phi from here, from here, and here also. So through all elemental surfaces we have to find out electric flux, and then you have to sum over the entire surface, or you have to integrate this thing d phi over this whole surface. So I am considering here d phi is through this surface element, d phi is through this surface element, d phi is through this surface element. Since these surfaces are oriented in different directions, so we cannot take here single area vector. There are many area vectors here. For this circular face, area vector is in vertically upward direction. For this lower bottom, area vector is vertically downward direction. So this curved surface, it is directed in many directions, okay. So curved surfaces or some curves from curved surface element, area vector of surface element will be here or here or here or here. Okay, so here and backward direction also. So there are many directions. Okay, so total flux from the closed surface is what? This is total flux. Phi total is what? Closed integral E dot ds. Means E dot ds is it is integral over the whole closed surface. So this is there. Now on the circular faces you can see electric field and area vector, they are directed perpendicular to each other. So circular here 90 angle 90 degrees there. So we can write here. Okay. So curved E dot ds here, E ds cos theta everywhere, E ds cos 0, you can write E ds cos 0 degree, because everywhere on the curved surface electric field is perpendicular to the surface, as we have seen here. So Gaussian surface is here and electric field direction is perpendicular to the curved surface everywhere, and it is parallel to the vector element or vector area of surface elements. So everywhere this electric field on the curved surface is parallel to ds, or you can say this surface element is perpendicular to electric field, or you can say electric field is perpendicular to the surface element. So surface element is perpendicular, but area vector is parallel to the electric field. So theta, angle between E and ds on the curved surface is how much? 0 here, plus E ds cos 90. Okay, where on circular face, and here also plus in the same way. Okay, E ds cos 90. Okay, this last point may not be visible in the video, but you can see there. Okay, you can find there. Okay, so E dot ds here, E ds cos 0 is 1 and curved. Okay, and this thing is what? Cos 90 is 0, cos 90 is 0. So both of these terms will give 0. So here curved surface is left. And in this also, what is happening according to symmetry? See, this curved surface is very symmetric to the distribution. So strength of electric field, or you can say magnitude of electric field, it will be same at all points of the surface, curved surface. Means at this point, at this point, at this point, and this point, these points are at the same distance from the distribution, and there is a symmetry. So electric field at all points on the surface, curved surface, will be same. So values of so let us write here. So as the symmetry suggests, okay, as the symmetry suggests, okay, magnitude of electric field is same at all points on the curved surface. Okay, so you can take out this E from this integration. So phi equals E is now constant, and this ds is now curved surface. Okay, so ds is what? Area element, a surface element, of curved surface, and the total curved surface you can write here. It should be how much? E equals, remember you are finding out E, and E is not the value of electric field due to point charge. You are considering charge density here, and E is unknown here. You have to find out. So integration of ds, all ds on the curved surface. So we have to leave these surfaces, circular faces. So this is what? 2 pi r l. Okay, r is radius of cylindrical surface. So 2 pi r l. And so this is 2 and 1. I have erased this thing here. I had written q enclosed upon epsilon naught. Okay, so lambda l was there. So lambda l upon epsilon naught, it was written like this. So this was 1. Okay, I have erased this thing. So remember this thing. So compare, you can compare 1 and 2 in each and every case of calculating electric field or finding electric field. You have to do this thing. First write the electric field, or write the electric flux according to Gauss law. So identify first the enclosed charge. What is enclosed charge by the Gaussian surface? So after identification you can write total flux. Okay, total flux is phi equals charge enclosed upon epsilon naught. So this can be written according to Gauss law. And then you have to calculate flux, means flux through surface element ds is d phi e dot ds. So you have to consider this thing in each and every case of finding electric field. Then this thing is summed over or integrated to find out total flux. So total flux is here, phi equals E dot ds, and how much? This is total flux calculation, and finally we reached to this point, phi equals E 2 pi r l, and in different distribution it will, this value may be different, will be different. Okay. So same total flux is here in equation 2 and equation 1. This was according to Gauss law. So compare these two from equations 1 and 2. So comparing equations 1 and 2. Okay. Comparing equations 1 and 2. Okay. What should be written? So flux phi, so lambda, okay, E 2 pi r l equals lambda l divided by epsilon naught. So l will be cancelled here. Electric field intensity at point P, means at the distance r, you know, because this field is taken at the distance r only, and electric field value at E is here at this point, and this value is also here and here. So one thing is clear, electric field at this point is here. So electric field, so lambda upon 2 pi epsilon naught r. Here remember, this is not 4 pi epsilon naught, okay, this is 2 pi epsilon naught r Newton per Coulomb. So this is about linear charge distribution. So this is completed now. Thank you for watching here, and remember, if there is any doubt, please you convey me, and cooperate with sufficient amount of energy, or cooperate. Thank you very much. Okay.